Let's look now at section 8.4 and talk about trigonometric substitution. So far, we've seen U substitution as the primary method of integrating all but the most simple expressions. However, U substitution is not the only kind of substitution that we can use. In this section, we're going to be looking at how to use substitutions of trigonometric functions and then exploiting the identities and properties of those trigonometric functions to simplify and integrate some more complicated looking expressions. So let's begin by looking at the kind of expressions that are going to warrant us using these kinds of substitutions. Whenever you have integrals that involve, and there's going to be three of them, if your integral involves the square root of a constant squared minus a variable squared, if your integral involves a constant squared plus a variable squared, or if your integral involves the square root of a variable squared minus a constant squared. Notice these are almost the same, but these are reversed. Here, this is a sum instead of a difference like those. If you have an expression that looks like this, then what we want to do is use the substitution U is equal to A times the sine of theta. Now that may seem a little arbitrary, but in a moment we'll see not only why that's a good selection, but also how to keep that straight to make sure that we know what is paired with which. Here we're going to be using the substitution given by U is equal to A times the tangent of theta. And in this case, we're going to have to use the substitution U equals to A times the secant of theta. Now, the question is, why would we want to use that kind of substitution? What does this have to do with this expression? Well, the quickest way to answer that is through an illustration. Consider a triangle. After all, we are using trigonometric substitutions. Using trigonometric expressions, you would expect either a triangle or a unit circle to be used in the explanation thereof. So let's imagine we have a right triangle. Okay, well, now consider these two sides, or rather, let's consider these three sides to involve this expression. Well, notice the square root of a squared minus u squared. That looks like using the Pythagorean theorem to do something, right? After all, if I were to say this equals to some value, let's say, b, for the sake of argument here, I could square both sides and I can say a squared minus u squared is equal to b squared. But then adding the u squared over would give me a squared is equal to u squared plus b squared, which, in spite of the fact that I'm using different letters, is the Pythagorean theorem. The two short sides of the right triangle squared and added together give me the square of the longer side. Here, note that if I'm taking a squared and subtracting from it, that must mean a squared is guaranteed to be bigger. So that means that a must be the length of the longest side of my triangle. Or in other words, it must be my hypotenuse. Here, I'm subtracting u squared away from a squared, which means u must be the side, either this one or this one. We're going to go ahead and choose this one. We'll see why in just a moment. And if I have this, by the Pythagorean theorem, this side must be the square root of the hypotenuse squared minus one of the side lengths squared, like this. So this expression that appears in my integral is going to appear in this triangle. It's going to be one of the short sides. Okay, well, now consider an angle in this triangle. I'll take this angle theta. Okay, well, I am trying to get away from using this. This looks complicated. Well, if I have these two pieces of information, then this third one is just generated from those two. So instead of worrying about this piece of information, let me use these two. Okay, well, these are the side opposite and the hypotenuse of a right triangle. Oh, okay, so then that must mean that, well, opposite over hypotenuse, that's the sine of theta. So that means that the sine of the angle theta must be the side opposite, u, over the hypotenuse, a. And if you multiply both sides times a, we get a sine of theta is equal to u. Okay, a sine of theta is equal to u. So that's one way to keep this straight. That's one way to interpret the substitution, and that is here is one length of a triangle. Okay, well, if that's the side of a triangle, from this information I can find the hypotenuse and the side opposite of the angle theta. But once I have this angle theta in consideration with respect to these two, I can say the sine of theta is equal to u over a, and so that gives us this substitution. Note that this substitution, when placed in here, will simplify this expression significantly once we employ the Pythagorean identities in the integrand to simplify using this triangle. I mentioned here I wanted to put u here and not over here. Why not over here? Because right here, opposite over hypotenuse, that's the sine of the angle theta. If I put u over here, that would be adjacent over the hypotenuse. That would be the cosine of the angle theta. And you say, yeah, so what? Well, instead of a sine of theta equals u, we would have had a cosine of theta is equal to u. What's wrong with that? Well, there's nothing wrong with that. But keep in mind, if this is a substitution, we're going to need a differential here in a moment. So if u is equal to a sine of theta, then du would be a cosine of theta d theta. If I had used a cosine of theta first, the derivative would have been a times negative sine of theta. Or in other words, the differential would be negative a sine of theta d theta, and then there's an extra negative to keep track of. So there's nothing really wrong with doing it the other way around, but this way makes it a little simpler because there are fewer negatives to worry about. In fact, there's no negatives to worry about here. Okay? We'll see an example in a moment of how this substitution actually does make this problem simpler. But before we do, let's go ahead and do the same thing for these two. Notice that's the sum of the squares of two sides of a triangle. That must be the hypotenuse. So this must be the hypotenuse, the square root of a squared plus u squared. So here a and u must be the sides of this triangle. A squared plus u squared under a square root. Okay, so then here I'll designate this as u and designate this as a. Call that the angle theta. And so now opposite over adjacent side, that's going to be the tangent of theta. So tangent of theta is equal to u over a. And of course, if I multiply both sides by a, I do get this substitution over here. So that's where that substitution is going to come from. U is equal to a tangent of theta. That'll represent this expression using this angle and the two sides adjacent to it, opposite and adjacent to it. U is equal to a tangent of theta. So that means that du is going to be a derivative of tangent is secant squared of theta d theta. The reason we use this orientation, u and a, instead of a and u, is for the same reason that I chose the orientation up here this way, because if we flip that around, instead of tangent, that'll be cotangent. And when I take a differential, when I take a derivative of tangent of theta, I'll end up with an extra negative in the differential. So it's not that it's wrong to do it the other way, it's just more convenient to do it this way. So this is the one we usually stick with. And finally, for this third illustration, again, I'll have a right triangle. Here, this is almost the same as this one, except instead of saying a squared minus u squared, where a is the longest side, here it's u squared minus a squared. Okay, so u must be the longest side. All right, so that's my hypotenuse. Here, I'll call this one a, and I'll call this one square root of u squared minus a squared. Again, that one's got to be u because it's the longest side, so that must be the hypotenuse. Here, these can go in either orientation, but the way we've chosen it here to have a on this side rather than on this side will again make things a little bit nicer because we'll have fewer negatives to worry about. If right here you had these backwards, you would still get a valid substitution. It's just one that's slightly harder to use. And well, these things are already complicated enough as they are. So this pen is about to die on me, isn't it? Let's see here. If there's any doubt that I do go through a lot of ink with these lectures, well, there we go. This pen was brand new 2 weeks ago. Oh well. Fortunately, they come in a 4-pack. So here we go. Let's see. So that's going to be the side adjacent. That's going to be the hypotenuse. Okay, well, that's going to be the cosine. Oh, yeah, but we said cosine is annoying to use because the derivative of cosine is negative sine of theta. And I don't want to deal with negatives. Well, okay, but no one said I had to have adjacent over hypotenuse. What if I do hypotenuse over adjacent? Oh, well, that's secant. Okay, so that's the choice that's typically made. Again, it's not wrong to choose in the other direction, but this is the one that's usually made for convenience sake. In this case, the secant of the angle theta is equal to the hypotenuse over the side adjacent to the angle theta. So it's going to be u over a, and just like in all the other examples, we multiply both sides by a, and we get our substitution. U is equal to a secant of theta, which means du is going to equal to the derivative of secant of theta is secant of theta, tangent of theta. So that'll be a secant theta, tangent theta, d theta. Any other choice of orientation here, having these flipped around or using cosine rather than secant, those are all perfectly valid, but here, this is the only one that does not require any extra signs, any extra negatives. Right? So here are our substitutions. Here are some mnemonics. Remembering these triangles is a good way to help you remember how these substitutions work, how they're oriented. And there's another reason we want this triangle we'll see at the very end. A bit of a spoiler. It has to do with back substituting. If you think about u substitutions, first you form a substitution, and then you integrate, but then at the end you got to back substitute to the original variable. These triangles are not just a nice mnemonic to help you remember how these are derived, but probably more importantly for application, these triangles are used to back substitute, as we'll see here in our problems. So let's begin with an example. And we're going to integrate x to the third over square root of 16 minus x squared dx. Okay, that is nightmarish. That is absolutely terrible. There is, at least to my knowledge, there is no algebraic trick to help you with that one. If there is, it's one that's substantially beyond the normal curriculum of any undergraduate math student. This is something that's just not nice to work with, algebraically, analytically, or in any other way. So we do note that we have this pattern right here. This is going to be a constant squared minus a variable squared under a square root. The fact that that happens to be in the denominator or in a numerator won't really bother us. The fact that this pattern appears at all suggests that this substitution is what we want to start with. So we're going to substitute. Note that 16 minus x squared is the same as saying 4 squared minus x squared. So that 4 must be your a, and that x must be your u. So what we're going to do is we're going to substitute. We're going to take u is equal to a. Or actually, I should say, well, let me just write that down. U is equal to a sine of theta, but we know what u and a are. So here we're going to take this x is equal to, we're going to take this 4 sine of theta. Now, at first, people will say, well, okay, but what's theta? That's the thing. We don't know, nor do we particularly care. We're never going to actually find this value of theta. It's a stepping stone. It's there to just help us in the integration. We don't actually care what its value is. It's not there to begin with, and it won't be there at the end. So we know u and a. This theta will forever remain a mystery, and that's perfectly fine. We don't really care what it is. All right, so now with this substitution, we're going to end up with the integral of, notice this x is that x and that x. So all we're doing is we're substituting things in. We're saying x equals 4 sine of theta. Okay, so plug it in there and there. So 4 sine of theta, and that's being cubed, over square root of 16 minus 4 sine of theta, and that's being squared. And then don't forget your differential. Here, dx, that's going to be, if x is equal to 4 sine of theta, that means dx has to equal to 4 times the cosine of theta. You can either take the differential from here, or you can remember this. Hey, 4 cosine of theta. 4 cosine of theta, d theta. So you can either find the differential from this x substitution, or you can just remember what happened up here. Either way, you get the same thing. So this gets replaced, but so does dx. 4 cosine of theta, d theta. And now you see why in the last section we went through and made sure we knew how to integrate trig functions, because that's what is required here. Before we start integrating, there's some stuff we can simplify. So let's write this out as, 4 to the third power, that's 64, times another 4, that's 256. So 256. I have sine of theta to the third. Okay, so sine to the third of theta. I have a cosine of theta as well. Okay, cosine of theta, d theta. Okay, in this denominator, we have square root of 16 minus 16 sine squared of theta. Notice now that this can be simplified via the Pythagorean identity. After all, we can write this as, and I'm going to write one more step than people usually write. Oops, I'm not sure why I wrote a minus there. Sine cubed of theta, cosine of theta, d theta. There's a common factor of 16. So I can factor that 16 out, leaving me 1 minus sine squared of theta. But now, by the Pythagorean identity, that's just cosine squared of theta. So this is equal to the integral of 256 sine cubed of theta cosine of theta d theta over the square root of 16 times cosine squared of theta. And now that's a perfect square. I can take the square root of that. So I can now write this as the integral of 256 sine cubed of theta cosine of theta over, that's 4, that's cosine of theta, d theta. And now some things simplify. Hey look, cosine of theta divides cosine of theta, and that's just equal to 1. And I can take 256 and divide it by 4, and that's just 64. So now that's 64, common factor. I can go ahead and pull that out. And that's going to be 64 times the integral of sine cubed of theta d theta. And we know exactly how to do that. So now we're dealing with an integral of an odd power of a sine function. So now we're going to take a single copy of that and strip that off. So that'll be 64 integral of sine squared of theta times sine of theta d theta. We're going to rewrite this using the Pythagorean identity. That'll be 64 times the integral of 1 minus cosine squared of theta sine of theta d theta, like that. And now we can distribute that out to give us 64 times the integral of sine of theta d theta minus the integral of cosine squared of theta sine of theta d theta. Oh, but those are both ones we know how to do. Here, we can write that as, here this whole thing is being multiplied by 64. Right? The 64 will distribute throughout. So that's going to be the integral of the sine of theta d theta. Well, that's going to be negative the cosine of theta d theta. Oh, not d theta, just negative 64 cosine of theta. And then here, if we're going to integrate cosine squared of theta sine of theta d theta, that's just going to be negative cosine to the third of theta over 3. After all, that is the negative derivative of the cosine of theta. So here, that's going to be negative cosine to the third, but then there's another negative out there. So that'll be plus 64 cosine to the third of theta over 3, plus some constant of integration. But now notice that we're in the wrong variable. We've integrated, but we've gotten a result with respect to theta. Our original question was with respect to x. Okay, well now we have to back substitute. Well, yeah, but how do I do that? Like, how do I get this to go back in terms of x? That's where this illustration comes in. I'm going to go ahead and replicate this illustration, but using the numbers that are specific to this problem. We're going to have this right triangle here. We'll call that theta. Here, we're going to put our value of a in the hypotenuse. Well, we saw that a was equal to 4, so I'll put that right there. And then we have this as our value of u, which in this problem, u was just x. So I'll put that there. And then this is the offensive expression, 16 minus x squared. Like that. Okay, so coming back down here, I'm looking for the cosine of theta. Well, that's theta. What is the cosine of theta? Well, cosine is the side adjacent divided by the hypotenuse. Yeah, that divided by that. So going back into the original variable, we can write that as negative 64. Instead of cosine of theta is the side adjacent over the hypotenuse. That's square root of 16 minus x squared over 4 plus, that's going to be 64 thirds cosine of theta cubed. So it's going to be that same expression, but being cubed. Just like that. But now, this can all be simplified, and we'll get our answer. All right, so let's see here. 64 goes into, 4 goes into 64 16 times. So that's going to be 16. And same thing over here, that's also 16. Okay. Here I have a 16. And square root of 16 minus x squared is a common factor. Oop, I'm forgetting my constant of integration here. So I'm going to go ahead and factor all those things out. So I'll be left with 16 square root of 16 minus x squared. And then that is being multiplied by, well, once we factored all that out, that's just a minus 1 right here. And then this expression here, I'm left with 3 in my denominator. And since I already factored out one factor of this, I'm left with this squared. So that's just going to give me 16 minus x squared. But then here I have a minus 1 left over since I factored everything else away. And so that's going to be 16 minus x squared minus 1, which will give me 15 minus x squared plus our constant of integration. And that is our result. All right, so let's see another example of that. Let's see here. Let's see if we can't put up a little bit of shade here. That's a little better. And, oh, actually looking at this, I have made a mistake. I forgot about my number 3 here, didn't I? So let's see, that's going to be negative 16 times that square root. Here I divided these out. I forgot about dividing by 3 here. So let's see here. That's, yeah, I forgot about my 3 here. So when I factor out that 16 square root of 16 minus x squared, I'm left with, oh, let's see, that'll be square root of 16 minus x squared. And here I'm left with, that's just minus 1, since everything else has been factored out, minus 1 plus, and then 16 square root of 1 minus x squared is gone, but you're still left with, you see what you see the kind of mistake one makes when the sun is in one's eyes? This is 4 to the third power, not just 4. So here, let me go back one step. Rewriting that line, we had negative 64 square root of 16 minus x squared over 4 plus 64 over 3 square root of 16 minus x squared over 4 cubed plus a constant of integration. So that's where I was before I started incorrectly simplifying things here. So I've just rewritten this in blue again here. All right, so now let's go ahead and start simplifying correctly this time. That'll be negative 64 over 4. Let's put those together. Square root of 16 minus x squared plus, here, let me cube everything. So this will be 16 minus x squared. That's that squared, but then we have one more square root of 16 minus x squared to work with. 4 to the third power, that's 64. And then that's 64 thirds over here. So I've cubed the numerator, cubed the denominator, and here I just move that one over. And now some stuff will divide away. 64 divides 64, so that's completely gone. Negative 64 over 4, that reduces to negative 16, just like that. And so now we're left with negative 16 square root of 16 minus x squared plus, this is going to be over 3, and that's going to be 16 minus x squared over 3 times the square root of 16 minus x squared, like that. So it looks like I don't have 16 as a common factor to the entire expression. Since that is completely gone, here I only have this as a common factor. So I can write that as square root of 16 minus x squared times negative 16, that's been factored out, and then that's been factored out, leaving us 16 minus x squared over 3. And then here we can give these a common denominator. So that's over 3, and that's 3 there. So that will be positive 16 minus 48. That'll give us negative 32. Right, okay. So that'll give us square root of 16 minus x squared. And that'll give us negative 32 minus x squared over 3 plus a constant of integration. And then here, there's a common factor. Everything's being divided by 3, and everything has a negative in front. So here, we can even write this as negative square root of 16 minus x squared over 3 times x squared plus 32 plus some constant of integration. There we go. Yeah, my apologies. That simplification before was incorrect. I essentially forgot to, or neglected to, raise this 4 to the third power, which causes this to be incorrect. So the simplification is correct now. All right, and so there we go. Note that our final result is not in trigonometric form. It actually is an algebraic expression involving a square root. And notice that we never did find out what theta was, nor did it really matter. So let's take a look at another example, hopefully one that's simplified correctly this time. Let's try the example, the integral of 1 over x square root of 9x squared plus 1 dx. Okay. If this was all in the numerator, you would just use a substitution. You would take 9x squared plus 1, you call that u. That means the derivative of this radicand would be 18x. So the differential would be 18x dx, and here you have an x dx to work with. So if this was in the numerator, if it was just integral of this dx, then you would use a u substitution. But the fact that this is in the denominator means that that is no longer valid. What we do notice instead, though, is you have the sum of a variable squared and a constant squared. The sum of a variable squared and a constant squared, which means we're going to be using a substitution, u equals a tangent of theta. All right, so here we go. Our u is equal to 3x, because after all, that's the variable expression that we squared to get this term. A is just equal to 1, because after all, 1 is what you square to get this term. And so putting this together, we're going to get that u equals a tangent of theta. And again, we knew that's the correct one because that's going to be the sum of squares, which for our problem means 1 times the tangent, is going to be 3x equals 1 times the tangent of theta. So that's your u, that's your a. So we could write 1, but we usually just don't write anything. So that's just 1 times the tangent of theta. Here, we generally want to simplify in terms of x, so it may be useful to us to just go ahead and divide everything by 3. So here we can say x is equal to 1/3 the tangent of theta. If you leave it this way, that's fine. If you write it this way, that's fine too. They both mean the same thing. Here, if x is equal to 1/3 tangent of theta, that means dx is going to be 1/3 secant squared of theta d theta. Just like that. So now this integral is going to become the integral of 1 over this x, is that x, is 1/3 tangent of theta. Square root of 9 times, again, that same x is going to be 1/3 tangent of theta, but that's being squared, plus 1. And now our dx is going to be 1/3 secant squared of theta d theta. So that's 1/3 secant squared of theta d theta. All right, so let's start simplifying. First of all, those 1/3s go away. 1/3 divides a third. And in here, notice that's 1/3 squared is 1/9. That's going to be 1/9 tangent squared of theta, and this 9 and this 1/9 will go away, leaving us just secant squared of theta in the numerator, tangent of theta outside of this radical in the denominator, and inside, that's just 1 tangent squared of theta plus 1. But by the Pythagorean identity, tangent squared of theta plus 1, that's secant squared of theta. So that's integral of secant squared of theta over tangent of theta, square root of secant squared of theta, d theta. And so here we can write this as secant of theta divided into secant squared of theta. So that'll be the integral of secant squared of theta over tangent of theta secant of theta, d theta, like that. And now these divide out to give us the integral of secant of theta over tangent of theta, d theta. Here, we've seen that there are several cases of integration that involve secant and tangent, and when it doesn't fall into one of the nice categories, the simplest thing to do is write everything in terms of sine and cosine. So secant of theta is 1 over the cosine of theta. Tangent of theta is 1 over the, sine of theta over cosine of theta. And now cosine of theta divides cosine of theta to just give us 1 over sine of theta d theta. But by definition, 1 over sine of theta is the same as the cosecant of theta. So that's the integral of the cosecant of theta d theta. And we know the integral of that. We end up with the negative natural log of the absolute value of cosecant of theta plus cotangent of theta, plus a constant of integration, like that. Now here, that's our result, but that's in terms of functions of theta. We don't want functions of theta. We want to go back in terms of x. So let's go ahead and go back using our triangle. After all, we have this expression here, 9 minus x squared plus 1 under a square root. That has to be the hypotenuse of some triangle. That's that longest side, right? It's the sum of two squares. So I would have a triangle, a right triangle with an angle theta. That expression, square root of 9x squared plus 1, goes there. And then we would have u and a. Note that for our problem, u was equal to 3x. U was equal to 3x, so that'll go here. And a, which was the number 1, that'll be the remaining side. Okay. So this triangle represents this expression. But now, with that triangle, we can express anything that we like, any trig function of theta with respect to these three side lengths, or in other words, with respect to x. So, to remind ourselves of what our expression was, we are left with the negative natural log of the absolute value of the cosecant of theta plus the cotangent of theta plus a constant of integration. But now we can go ahead and convert back into expressions of x, because we know the cosecant of theta, well, that's going to be the reciprocal of the sine of theta, or in other words, it's going to be the hypotenuse over the opposite. So that's negative natural log of the absolute value of cosecant of theta is the hypotenuse of the triangle over the side that's opposite of that. So that's going to be 3x. Plus the cotangent is the side adjacent to the angle divided by the side that's opposite, plus a constant of integration. And here, if you want to merge these together because they have a common denominator, that's usually the way it's written. So that's going to be square root of 9x squared plus 1 all over 3x plus a constant of integration. And that's our result. Incidentally, this simplification here, where we said, okay, square root of 9x squared plus 1, that x is being replaced by 1/3 tangent of theta, that's being squared, and then we use a Pythagorean identity. Then we take the square root of that identity, and that gives us secant of theta. This is an algebraic way of doing that. You substitute, well, I guess algebraic and trigonometric way of doing that. However, as long as you can keep it straight, there is a more visual way of doing that, of jumping from here to here. And again, it has to do with our triangle. This square root of 9x squared plus 1, remember, that is going to be one side of our triangle, in this case the hypotenuse, but in any of these substitutions it will be one of our side lengths. Okay, well, if that's one of our side lengths, I should be able to express it using a trig function. So coming back to my illustration, right here, this is square root of 9x squared plus 1. Notice if I divide that by 1, that's going to be the side, the hypotenuse, divided by the side adjacent of this angle theta. Or in other words, it's going to be the secant of this angle theta. So secant of the angle theta is equal to square root of 9x squared plus 1. Oh yeah, that's what we got. That square root of 9x squared plus 1, that eventually became secant of theta. That eventually became secant of theta. In our previous problem, we solved pretty much the same thing. Well, not pretty much the same thing, exactly the same thing. Here, we had square root of 16 minus x squared. Okay, well, that's that part right there. Okay, so if I take square root of 16 minus x squared, if I divide that by 4, unfortunately I can't use 1 because 1 is not one of the sides of a triangle, but 4 is nice. It's a constant, at least. I'd rather not use a variable. If I take this divided by this, well, that's the side adjacent divided by the hypotenuse. So notice, I think I'm trying to express the complicated expression into a radical. I'm going to divide it by whichever remaining side is constant. So in this case, that's going to be the adjacent over the hypotenuse. Oh, well, then that's going to be the cosine of the angle theta. Well, multiply both sides by 4. Okay, so then square root of 16 minus x squared, square root of 16 minus x squared, will be replaced by 4 cosine of theta. Hey, it eventually got replaced by 4 cosine of theta. That seems like a nice, simple thing to do, and it can be, but it's also an easy way to get yourself confused if you're not familiar with these kinds of techniques and with these kinds of visualizations. So here I'm showing you this in hopes that you will be honest with yourself and go with whichever technique you can deal with. Some people are more capable of handling visualizations and interpreting data from the illustration. If that's the case, hey, that's a nice, quick way to do it. However, it doesn't matter how quick something is if it's wrong. So if you're having a hard time visualizing that or having a hard time seeing how this connects to this, then follow the trigonometry. It may take you an extra 1, 2, 3 steps, but it'll be correct. So just keep that in mind. All right, so let's take a look at one more example. So far we've seen an example of substituting with a sine of theta, with a tangent of theta. Let's look at one more. So let's consider now the integral of, this one won't have a rational expression in it. This one will not have a numerator and denominator. It'll look just like this. X to the third square root of x squared minus 9. Okay. If this was just an x on the outside, this would be nice because I would have a u substitution. If this was an x squared on the outside, it would be almost as nice because I could use a change of variables. I could say let x squared minus 9 equal to u, and this would become square root of u, and this would be u plus 9. And things would still be nice. But with a third power out here, well, that's not a nice thing to do, either by u substitution or by a change of variables. But we do note that we have the difference. We have a variable squared minus a constant squared. Okay, I have a variable squared minus a constant squared. I'm going to use a substitution. U is equal to a secant of theta. So here, I'm going to take u is equal to that x, because that's the variable that's being squared. I'm going to say my a, that's 3, because that's the constant that's being squared. And then, using this bit of information, we're going to use the substitution a is equal to the, u is equal to a times the secant of theta, which in this problem is x equals 3 secant of theta, like this. Okay. Let me go ahead and draw out my triangle from the very beginning. I know I'm going to need this eventually, so let me go ahead and do that now. I'm going to have a right triangle. I'm going to call this the angle theta. And using our visualization from the beginning of the section, we see that the offensive term is here, opposite of the angle theta. U is going to be our hypotenuse, and A is going to be the side adjacent to the angle theta. Okay, so the U is going to go here. The A is going to be adjacent. And then this offensive expression, the square root of all that other nasty looking stuff, that's going to be opposite of the angle theta. So I've just replicated this triangle with x and 3 in place. All right, so one last thing. If x is equal to 3 secant of theta, we're going to need a differential. After all, we are replacing everything with respect to u instead of with respect to x. So, with respect to theta rather than with respect to x. So if x is equal to 3 secant of theta, then dx is equal to 3 secant of theta, tangent of theta, d theta. And now we are prepared to begin our substitution. This is going to equal to the integral of x is being replaced by 3 secant of theta. Okay, so that's going to be 3 secant of theta, but don't forget that's being cubed. Now here, we could use this visualization. We could say, well, look, if I take the square root of x squared minus 9 and I divide it by 3, that's going to be the side opposite divided by the side adjacent. Oh, that's the tangent of the angle theta. Oh, but now if I multiply both sides by 3, that'll isolate this square root. So that'll be square root of x squared minus 9 is equal to 3 tangent of theta. So right here, this expression, we can replace it with 3 tangent of theta. Now, if you're okay with that visualization, awesome. You just go ahead and replace that with 3 tangent of theta right now, and we're done. If you're not comfortable with that visualization, of course, we can always do it analytically. You can just pop in some results here. 3 secant of theta, that's going to be our x. So we're going to square that. Minus our 9. Now, if we square this, I'll put the dx at the end there. That's going to be 3 secant of theta quantity cubed, square root of, that's 9, secant squared of theta minus 9. Our dx is going to be 3 secant of theta tangent of theta d theta. 3 secant of theta tangent of theta d theta. And so here, that's going to be the integral of 3 secant of theta quantity squared, square root of, we factor out a 9 here, that's going to be 9 times, we'd be left with secant squared of theta minus 1. Oh, but by the Pythagorean identity, secant squared of theta minus 1, that's tangent squared of theta, times 3 secant of theta tangent of theta d theta. Oh, but now that's a perfect square. So if I take the square root, that's going to give me 3 secant of theta, quantity squared. And now the square root of 9 is 3, and the square root of tangent squared of theta is tangent of theta, which was what we were expecting. That square root of x squared minus 9 gets replaced by 3 tangent of theta. If you're comfortable with that visualization, you can jump directly from here to here. If not, well, it's going to take 3 extra steps, but it'll be correct. So do the simplest technique that gets you the correct answer. So here that's going to be 3 secant of theta cubed times 3 tangent of theta times 3 secant of theta tangent of theta d theta. And now a bunch of things simplify out. So let's see here. That should be a power 3, like that. Okay, start off as a power 3. Okay, so let's go ahead and cube stuff. That's going to be 3 to the third is 27 secant of theta times 3 times tangent of theta times 3 times secant of theta times tangent of theta d theta. I have a bunch of constants. 27 times 3 is 81. 81 times 3 is 243. So let's go ahead and take all that out. 243 times the integral. I have secant of theta times secant of theta. Well, that's secant squared of theta. And I have tangent of theta times tangent of theta. Oh, that should be a cube, shouldn't it? I have secant cubed of theta times another secant of theta. That's secant to the fourth of theta. And then I have a tangent of theta here and another tangent of theta here, which is tangent squared of theta d theta. And now that's something we can integrate. Notice you have an even power of secant. So we can write this as 243 integral of secant squared of theta, tangent squared of theta, secant squared of theta d theta. And now, as we saw in one of the cases in our previous section, we're going to save this as our differential. And so we want to write everything else in terms of tangent. Because after all, here we're going to take d, I'm not going to use u again because we already used u for something. Let's say dw. If that dw, my differential, is going to be secant squared of theta d theta, that means that the original w had to be something whose derivative is secant squared of theta, which is the tangent of theta. So that's our differential. That'll be our dw. Everything else must be written in terms of tangent of theta. Okay, so here we can convert this into 1 plus tangent squared of theta using our Pythagorean identity. So we end up with 243 integral of 1 plus tangent squared of theta times the tangent of theta squared secant of theta squared d theta. And now using this substitution, normally I would call it a u substitution, but we've already used u for something, so a w substitution. Here we can write this as 243 times the integral of 1 plus u squared times u squared, w, right? dw. So 243, 1 plus w squared, that quantity, times w squared again, and then this expression is just our differential. That's our dw. So now we can distribute that, and that'll become 243 times the integral of w squared plus w to the fourth dw, and now that's something we know how to integrate. Notice we've used two substitutions. First a trig substitution and then a standard u, or in this case w substitution. And that's perfectly acceptable. Sometimes substitutions have to be performed more than once. Here we can write this as 243. Integrating this is going to give us w to the third over 3 plus w to the fifth over 5 plus a constant of integration, which I will worry about at the very, very end, like that. Here, this can be distributed out. 243 divided by 3 is 81. So that's going to be 81 w to the third plus 243 w to the fifth over 5. Again, plus a constant, which we'll worry about later. So now, that w is actually tangent of theta. So let's go back and substitute in tangent of theta. So now this is 81 tangent cubed of theta, that's being cubed, plus 243 over 5 tangent to the fifth of theta, plus our constant of integration. And you know what? It didn't really cost a lot of effort to just put a plus c there. All right. So now we're almost done. Note that we do have expressions in terms of theta. We're not back to expressions in terms of x yet, but this triangle will help us resolve that as well. We can take tangent of theta, and we can represent that using this triangle by taking the side opposite divided by the side adjacent of the angle theta. So that's going to be that square root over 3. So now this will become 81 times the square root of x squared minus 9 over 3, and that whole thing is being cubed, plus 243 over 5 times the square root of x squared minus 9 to the power 5 over 3. Oh, I guess the whole thing's to the power 5, just like that, plus our constant of integration. Things start to simplify out now. We can write this as 81. Here, 3 to the third power, that's 27, so that'll be over 27. If I take the square root of x squared minus 9 to the third power, that'll give me x squared minus 9 times the square root of x squared minus 9. All right, 2 of those make it so that the square root goes away, and there's 1 left over, plus 243 over 5. 3 to the fifth power, that's going to be 243, which is nice. That'll make everything completely go away. Well, actually not everything. Your denominator is still left. And now raising this to the fifth power, will give me x squared minus 9 times another x squared minus 9 times the square root of x squared minus 9. 2 square roots, 4 square roots, and one more makes 5 square roots. Plus our constant of integration. Some stuff will simplify here. Those are both gone. Here, 81 over 27, that's just the number 3, like that. And now I notice some common factors, namely this stuff right here. So I can write this as x squared minus 9 times the square root of x squared minus 9 times, with all this gone, we're left with just the number 3, plus, these are both gone, they've been factored out, and we're left with x squared minus 9, just that one, those two have been factored out, over 5, plus our constant. We can give both of these a common factor, a common denominator, so that we'll have a 1/5 as a common factor. Multiply top and bottom by 5, and so now that 5 is a common factor, so this will give us x squared minus 9 times square root of x squared minus 9. We're factoring out that 1/5 there, so let's go ahead and write that out front. Let's say 1/5 times x squared minus 9 times square root of x squared minus 9. And once that's gone, we have 15 minus 9. It's going to give us 6 plus x squared plus our constant of integration. So you see how our substitutions work. No one ever said they were going to be necessarily short, but they do give us a reliable way of integrating expressions that otherwise would not be accessible. Note once again that this illustration here is very useful because, yes, it does help us orient our substitutions in the first place. It tells us, okay, this goes there, this goes there. But at the end, it is also used to bring us back into our original variable. You use this illustration to back substitute to your final result. So let's go ahead and have you try one. All right, let's go with this one. We're going to take the integral of x over the square root of x squared minus 6x plus 5 dx. Okay. This one has one extra step that you need to do. Notice this is not either the sum or difference of squares. In every one of our substitutions that we've seen examples of, and even at the very beginning, everything was either the sum or difference of squares. Here, that's not the sum or difference of squares under the radical. Oh, but it can be if you complete the square. So here, the very first step is an algebraic one. Complete the square under the radical, and then you can go ahead and do the substitution, the trig substitution. So go ahead and give that a try. Pause the video, give yourself the time that you need, and once you're done, go ahead and unpause, and we'll go through it together. All right, so let's take a look. First of all, we're going to complete the square here. Okay, well, let's go ahead and complete the square. Let me just do this off to the side. X squared minus 6x plus 5. We're going to do that adding and subtracting what we wish we had. Here, this would be a perfect square if this had a plus 9 right here. Okay, so let's add 9. All right, because now that would factor out as x minus 3 squared. Well, yeah, but just adding 9, you can't do that. Okay, well then let's subtract 9 to balance things out. So now this will become x minus 3 squared, and then this is just negative 4. So our result of completing the square allows us to write this radicand as this squared minus that squared. So x minus 3 squared, and here I'm going to write it as minus 2 squared. So that's underneath the square root, just like that. So you note that you have variable expression squared minus a constant squared. That's going to be this substitution. Variable expression squared minus constant squared. All right, so we're going to be using this substitution. U is equal to a secant of theta. u is equal to a secant of theta, where u is what's being, variable expressions being squared, in this case x minus 3, and a is the constant that's being squared, which is the number 2, and putting that together, that's going to give us x minus 3 is equal to 2 times secant of theta, just like that. Here we can find our differential. We can find dx is equal to, note the derivative of a constant is 0, so that part won't bother us. This would be dx is equal to the derivative of 2 secant of theta, which is 2 secant of theta tangent of theta, d theta. That's our differential. And so over here, we can write this as the integral. This x is that x there. We can move the 3 over to the other side to isolate our x. So that'll be 2 secant of theta minus 3. Oh, sorry, that should be plus 3 since it's been added over. 2 secant of theta plus 3 over the square root of, that's going to be 2 secant of theta, but that's being squared. So I can write that as 4 secant squared of theta minus 2 squared, or in other words, minus 4. And then our dx, our differential, is now 2 secant of theta tangent of theta d theta. Which looks like that. Here, we can factor out the number 4. That gives us 4 times secant squared of theta minus 1. And since secant squared of theta minus 1 is one part of the Pythagorean identity, we can replace secant squared of theta minus 1 by tangent squared of theta. So here we write that as 2 secant of theta plus 3 over the square root of 4 times the tangent squared of theta times 2 secant of theta tangent of theta d theta. Just like that. And of course here, tangent of theta squared and 4 are both perfect squares, which we can take the square root of. So we can write that as 2 secant of theta plus 3 over, that's just 2 tangent of theta times 2 secant of theta tangent of theta d theta. A few things divide away now. 2 divides 2. Tangent of theta divides tangent of theta. And now this secant of theta can be distributed throughout those two terms. So now we have the integral, there's no more denominator, of 2 secant squared of theta, secant times secant, plus 3 secant of theta d theta. All right, so now we can go ahead and integrate each of these. Using linearity, we can split that as 2 times the integral of secant squared of theta d theta plus 3 times the integral of the secant of theta d theta. And we know the integral of secant of squared of theta d theta, that's just the tangent of theta. Plus 3, we know the integral of the secant of theta. That was that strange one. That's going to be natural log of the absolute value of secant of theta plus tangent of theta, plus a constant of integration. So now we are done with the integration of the trig functions, or of the trig expression here. But now we need to convert everything back into the original variable of x. So that's where our triangle comes in. That's theta. That's a 90-degree angle. All right. So using the illustration that we had before, we see that when this is the substitution to be used, a is the secant of theta, u is your hypotenuse, a is the side adjacent to that angle theta. So u, that x minus 3, that's in our hypotenuse, and a, that's the side adjacent. And then this third side is the offensive expression that we were trying to get rid of. We can write it either way. We can write it in its completed square form, or we can just write it in the original form. Both will be equivalent to each other. Like that. So there's your u, there's your a, and there's going to be the square root of u squared minus a squared. You could write it this way, u squared minus a squared, or you could actually distribute that out and get back to the original radican that you started with in the beginning. And they're both equivalent, both are fine. Because now we can use this triangle to give us these expressions. 2 times the tangent of theta. Okay, well, tangent of theta, that's the side opposite of the angle theta, divided by the length of the side adjacent to the angle theta. Or that's square root over 2. Square root of x squared minus 6x plus 5 over 2. Plus 3 times the natural log of the absolute value of secant of theta. Well, that's going to be the side adjacent, the angle theta, divided by the length of the hypotenuse of the triangle. So that's going to be 2 over x minus 3, plus the tangent of theta, which is the one we just saw. Plus our constant of integration. Here the 2's divide away. And, well, that's really about it, isn't it? That's as simple as that's going to get. And, oh, here, I have these backwards, don't I? Secant of theta is hypotenuse over adjacent. Here I wrote adjacent over hypotenuse. So these are backwards. That should be x minus 3 on top and 2 on the bottom. There we go. So I suppose we can combine those since you do have a common denominator. So in the end, we have square root of x squared minus 6x plus 5 plus 3 times the natural log of the absolute value of, since these have a common denominator, I suppose I can put them together, x minus 3 plus the square root of x squared minus 6x plus 5 over the common denominator of 2. Plus our constant of integration, which wraps up this result. Okay. So keep in mind that every once in a while, the original problem might not be either the sum or difference of squares under a square root. Sometimes you might actually need to complete the squared first. So here, we complete the square first, and then it fits the category of, oh, let's use the substitution u equals a secant of theta. The most common mistake people will make is that once they perform their substitution, they'll forget to include their differential. A lot of times people will include just this part and then just write dx as d theta, completely neglecting these extra factors. And so you're going to end up with something incorrect. So be mindful of that. Dx should not just be replaced with d theta. You're not just changing letters. Right? You're not just saying, oh, this symbol should be replaced by this symbol. No. This has a meaning. This is the differential with respect to x. This is the differential with respect to theta. But if x is equal to a function of theta, then the differential of x is the derivative of the function of x times the differential of theta. Think back to the definition of a differential back in Cal 1 to see why that can't just be replaced by this. You have to have the differential as the derivative of the function times the differential of your original variable. And so that brings us to the end of this section. If anybody has any questions, comments, or problems, please make a note of those and let me know. Go ahead and reach out to me during our next office hours, during our next meeting. And I hope everyone has a nice day.